Thank you, all of you, for being here today. For those of you that might not know me, my name is Raquel Alonso. I'm a PhD student at BEDAC, and I'm in my third year of PhD. So today I'm going to present my first article, which is under review in IEEE Transactions on Smart Grids. And it's a paper that I worked together with Pedro, who is my supervisor. And the main topic that we will be looking today is about interactions between energy communities and retailers. And the particular focus is on their effect on their balancing cost. So we all know that the power system was designed assuming that there's one direction of power from large generators towards the distribution grid at the end user level. And due to the boost of renewable integration, generation is no longer only connected to the transmission grid, but also on the distribution level, together with other what we call distributed energy resources, such as stationary batteries, EVs, or other types of appliances that can be regulated to provide demand response services. Despite the benefits that these assets provide to end users, or prosumers as we call them, we have seen that these resources can be better used if we group together consumers and prosumers together in what we call energy communities. And usually these are groups that work together towards a common goal that can be environmental, social, and usually economic. So this group of prosumers and consumers can be organized in very many different ways. And even though some of them are designed towards working in island mode, so not connected to the main grid, most of them still rely on the grid supply. So what this basically means is that they still rely on the supply from retailers, and they need still to be or to have a contract with these retailers. For those of you that might not be very familiar with the market, these retailers are basically the intermediary between the end users and the wholesale markets. So they purchase volumes to supply the end user demand. Up until now, these retailers had the task of forecasting the load of their customers in order to purchase volumes in the wholesale market. However, with the introduction of distributed energy resources, the forecasting is becoming very complicated because they don't know how these assets are going to behave during the day. So they are facing quite significant problems. And our hypothesis in this paper is that basically when these retailers don't have any information about these energy communities, first they will bid wrongly in the day-ahead market. Then they will have no visibility to correct these imbalances between the forecast and the real needs of their customers, which will mean that in the balancing settle or in the balancing stage, they will be deviated, that we will go deeper into it afterwards. And at the end of the day, this means additional costs for retailers. So,
sorry, what do you mean by no visibility?
Sorry?
What do you mean by no visibility?
They don't have information about how the assets are behaving. So they cannot react on real time and participate in the intraday market. That's what I mean. So now we know the problem. So basically what we are going to study here is how the energy communities are affecting the financial outcomes of retailers. And this is being discussed that can pose some, maybe not regulatory barriers, but at least some opposition from decision makers, because it can unbalance the market stability that is nowadays. Also, there's a gap in the literature in understanding what are the real effects of energy communities on these market actors. And also, we aim to propose alternative solutions between collaboration between these two agents. So in this paper, we design a framework that consists of 3 stages. The first one consists on a stochastic linear optimization of the retailer's decision in the day-ahead market. The second one is a deterministic linear optimization of the energy community to see how these communities are gonna behave. And then we have an ex-post analysis of the imbalance costs. This one is based on the European system, as I will explain in a second. And also, we will explore one collaboration strategy that has been proposed in the literature that is called data exchange markets. And we will see how this will match in this system. So before introducing the mathematical algorithms, I want you to introduce the balancing system a little bit better. So there are 3 stages. The first one is the balancing planning stage, which occurs before the real delivery. And basically here, what the retailers do is to participate in the day ahead, and they balance throughout the day in the intraday market to really or accurately purchase the volumes that are needed. And just before delivery, they have to send their position or their commitments to the TSOs. Then in the balancing service provision is actually when it's provided, the balancing. And here the TSO activates the reserves in order to balance out the real needs of the system, the whole system, and the commitments of those market actors that bid before. And then afterwards, some days after, we have the balancing settlement stage, in which basically the TSO calculates what we call the imbalance price. And basically this can be considered a penalization for those retailers that were unmatched with the real needs of their customers. However, in Europe, now it has been installed what we call a single price mechanism. I'm not gonna go too deep into it because it's a bit more complex, but the main idea here is that this mechanism is inducing what we call passive balancing services, which means that retailers can also get rewarded by being deviated. So even though they didn't match the real needs of their customers, they are earning some money back. Okay, that is the main idea. So yeah, basically by helping the system, they get additional benefits. Then now let's move to the methodology part and to the algorithms. The first model is the retailer, which basically here we are maximizing the expected profits from providing these passive balances that I explained you. And basically here the decision, the first state decision variable is the day ahead bid. Here we have made some assumptions, and it's basically that this bid is gonna be the final position in the market. That means that I'm not considering intraday opportunities for the retailers throughout the day. Also, we have full information of prices, and this is done because in the whole study, I don't want to capture the deviations caused by the forecasting of these prices, but I just want to investigate what are the actual impacts of communities on the retailer. And also here, the uncertainty that I didn't mention is based on the renewable generation of those households that belong to the community. If you have any question, we can take it afterwards because I don't want to go too deep in the mathematical, but yeah. Here we have the community model. It's a coalitional model in which basically all the households work together in order to minimize their total costs. These costs are coming from the grid imports, and they are priced based on a retail tariff that they have contracted with their retailer. And this optimization model is subject to some constraints, such as the balance equation at each node. Also, we have peer-to-peer trading. That means that each household can send their generation to other households. We have batteries as well, and also we have EVs. Here in the EV, also we incorporated rolling horizon techniques to improve the modeling. And then now we can move on to the case study. we applied this framework to a 50 household community, which we have real measured data, and is located in London. And we assume two types of tariff subscription for the community. One is the flat tariff, which is basically the same price throughout the whole year. And then we have real-time tariffs, which is a tariff that fluctuates according to the day-ahead price. And then based on this, we have 6 different cases. The two first ones are the business as usual or the baseline case, in which there's no community, and the retailer just have to supply the needs of individual households. There's nothing else. Then the next two are the home battery cases, and here we assume that there's a community, and this community can have peer-to-peer transactions, and the storage technology is stationary batteries. Okay, and we have 2 types of tariff subscription: the flat rate and the real-time. And similarly, we have the EV case, but instead of stationary batteries, we have EVs. So now let's move to the fun part. I will try to simplify a bit the results because of this terminology of surplus, passive balancing, etc. can be a bit messy. So just please stop me if there's some doubt, whatever. So here what we are seeing are the surplus and deficits of retailers throughout the whole year caused by the communities in the different cases that I have explained. So the first one is the baseline here. And here what we see is that there are some deviations. And these deviations are fully caused by the opportunity or the arbitrage opportunity that retailers have in the market. Okay, and they are operating towards it as described in the first model of the retailer. And then we have the home battery. And as expected, the introduction of stationary batteries, what is creating is surplus on the retailer. That means that the retailer, at the end of the day, end up with more production that the community needs. And also the small difference between real-time tariffs and feed-in tariffs comes from the reaction of battery to the volatility of prices. And then when it comes to the EV case, we see a different picture in which not only we have surpluses, but we also have deficits in the retailer position. This basically what means is that the EVs not only act as flexible sources, but also as an extra load for the retailer to cover. And again, the difference between the fixed tariff and real-time tariff comes from the arbitrage opportunity of volatility of prices. Then,
Okay. Just one question. Maybe I missed it, but you have home batteries and you have EVs, but do you have local production?
yes,
Okay.
in both cases.
In both cases?
Yes.
Okay. Because you didn't mention the two.
Yes. Yes, so the
Okay,
community
local
has,
production, yeah.
yes, the community has renewable production plus stationary batteries or EVs.
And the renewable production is PV or
PV and wind.
and wind.
Yes, we also consider. Sorry, and thank you.
And this covered 30% of the demand continuously.
Yes, the renewable production more or less, yes. So, as we saw in the balancing slide, deviations might mean that they benefit the system if they provide passive balancing, but also they can deteriorate. And here, this is what we are showing here. So the passive balancing rate identifies which deviations cause some benefit for the retailer and for the system, and the imbalance the opposite. And we can identify 2 things. First is that in both cases, so both the stationary batteries and EVs, have very similar passive balancing rates. So they help the system more or less in the same degree, despite the difference in deviation profiles that we saw in the previous slide. And also we see that even though we use real-time tariffs, the passive balancing rates are not improved for the retailer. So it's not a good signal for the retailer to ensure that their position is benefiting them. And then this has some financial consequences. In the home battery case, due to the less grid dependency from the community, the retailers are gaining less payments from the community, and this is the major effect for them, even though there are some benefits from passive balancing. So the passive balancing doesn't offset the losses from not selling enough grid supply to the community. And this ends up in a reduction of profit of 30%, which is pretty high. On the contrary, with the EVs, as they behave also as an extra load, plus the benefits of providing passive balancing, the retailers end up actually having more benefits than they previously expected. So here we can see that even though we have energy communities, just the setup of these energy communities might impact completely differently the profit results of retailers. And also this might make us think that retailers might be interested in knowing what is happening actually in the energy communities and gain some more information. So we studied the possibility of data exchange, in which basically here we assume that the retailer has full information of the community and they might bid perfectly in the day-ahead market, and they will end up not having any deviations. So what we see, the results here, I'm not going to enter into much detail because of the numbers, but basically what we see is that there's no benefits obtained by improving the bid of the market, basically because in the same way that they reduce their costs, they also reduce the revenues coming from the passive balancing, and therefore is not benefiting for them. And here we don't consider even the transaction cost, which might arise from establishing this collaboration. However, also another point that is important to mention is that even though this strategy doesn't help the retailer, it actually will help the whole system, as it will reduce the pressure on TSOs to balance those deviations from the retailer. So just to wrap up, basically we have seen that energy communities has a considerable effect on the deviations and the magnitude of retailers' deviations. And this would mean that in the future we can expect TSOs having more pressure in the balancing stage. Also, we have seen that different energy communities have completely different financial results on retailers. However, we also see that in general, there's not much penalization on deviating because of the mechanism that is implemented in Europe. And on the contrary, it can provide some benefits for retailers. And the biggest effect or negative effect for retailers comes from the lower grid dependency, and not from the penalizations of these deviations. And also something that we touched upon in the paper that I didn't have too much time to talk about, but is basically the idea of extending these balancing responsibilities on energy communities. And we discussed that this might not be a good solution, first of all, because end users might see this responsibility as a barrier for them to become part of a community. And also we have seen that it doesn't necessarily mean a large problem for retailers. So we discussed it. And also we saw that maybe the data exchange collaboration strategy that has been discussed in some papers might not be a good alternative for retailers who may need to seek for other types of business models ideas in the future. Thank you very much, and I will be very glad to answer any question.